Thanks, Professor Kim, for the introduction. I'm Richard from UC Berkeley, and I'll be talking about recognizing functions in. Sorry about that. I guess I need to plug this in again. Okay. So I'll be talking about recognizing functions in binaries with neural networks. This is joint work with my co-authors Don Sung and Reza Moazzezi, who are also from Berkeley. So since the title of the work, the talk starts with recognizing functions in binaries, I'll start out by going over exactly what that means and describe the goal that we want to achieve in this work. So we have some binary code that we would like to do some analysis on. And since functions are the building blocks of computer programs, we would often like to identify which parts of the code correspond to which functions. And we can use that as a basis for further analysis. However, the binary will often lack information about where functions are present because that information has been stripped away from it. So our job here is to recover this information by directly looking at the code. And in this picture on the side, we take in the stripped binary code at the top. We think about it for a bit, and then we've concluded that there are 3 functions and that they're located at these byte ranges that are marked on the slide. So I said that function identification serves as a basis for various analyses on binaries, and here's a short list of some of them. So as an example, let's take retrofitting control flow integrity. So we might want to take a binary and automatically add enforcement of control flow integrity to it, which is where we want to check before making a jump that we're jumping to somewhere valid. And since functions are a major cost of valid jump targets, in this case it seems pretty useful to know where functions are located in order to be able to do this. And here's a quote from a paper presented at USENIX 2 years ago, which was about this very topic of adding control flow integrity to existing binaries. So the authors say that they begin their technique by identifying functions so that they can build a control flow graph, but that without the metadata provided by a symbol table, it can be difficult to do this identification. That serves as the prelude to the entire rest of their approach. But you might still think, how hard can this problem be? So let's take this short C program as an example. On the left of the slide, it computes the greatest common divisor of 2 numbers using Euclid's algorithm. And when you compile this without any optimizations turned on, GCC produces the code that you see on the right. So this is the snippets of the 3 functions present in the binary. And all the functions begin with the same 2 instructions, push RBP, and then move RSP into RBP. And as you may know, these instructions are preparing the stack and base pointers for the body of the function. So it seems like a reasonable hypothesis that maybe you can just look for these instructions and conclude that when we see these instructions that there's a start to the function. But of course, the story isn't quite that simple. And some prior work that I'll get into the next slide actually reported that if you look for this push RBP instruction on 64-bit Linux binaries, you can only find about 1/4 of all functions. And you can get a sense of why it doesn't work very well on this side. Here we have the same code as before, compiled with more optimizations turned on. And the nice pattern we had before, where all the functions began with push RBP, is no longer present. And while push RBP is the sort of a thing that would happen obviously near the beginning of a function, something like, say, move EDI into EAX isn't something like that. It might occur anywhere. So it makes it pretty clear that we need a more sophisticated method to be able to find the functions accurately. So what has been done before about this problem? So at USENIX last year, there was this paper titled Byte Weight, Learning to Recognize Functions in Binary Code. In this work, they used a machine learning approach, which we could summarize as taking in a lot of binaries where we have the ground truth about the function locations, and then memorizing all the possible sequences of instructions that occur at the start of functions. And the authors did a very nice comparison with other research papers and also tools like IO Pro, and then they were able to be more accurate than either of them. And however, their approach required a bunch of preprocessing on the code, such as normalizing the disassembled instructions, and they also needed to do a bunch of expensive static analysis in order to obtain the full results that they report in the paper. So how do we use neural network to solve the problem of function identification? Recall that we start with some binary code like this, and then we want to find out where the functions are. So we start out by breaking it down into 2 simpler problems. So first, we try to identify the bytes of the binary where functions begin. We call this function start identification. And just having this can be enough for many purposes because a lot of analysis work by starting at the beginning of functions and proceeding from there. And then the other half is to identify the bytes of the binary where functions end. And on its own, this probably doesn't have much use, but we can combine it with function standardization to be able to find the binaries of functions, which is the goal that we set out to solve in this work. So the title of the talk, again, is about recognizing functions with neural networks. So we'll now go over some background on what neural networks are and how they work. So this is a pretty standard picture of a basic neural network. It's organized into these layers, which are grouped together with the dotted line boxes here on the slides. And each layer consists of a number of nodes, which are represented as circles in this picture. And within the neural network, so the computation proceeds from the bottom layer to the top layer. And the arrows between the nodes represent the weights, which determine how the layer below influences the layer above. So more concretely, let's consider the bottom two layers of the neural network in this picture, which are labeled X and Y. Each node, each circle holds one real number. So here X is a three-dimensional, or you can see X as a three-dimensional real-valued vector, and Y as a five-dimensional real-valued vector. And the weight W, as represented by the arrows here, is then a 5x3 matrix. We compute Y by doing a matrix multiplication of W with X, and then adding this B, which is called a bias, which is emitted from the pictures for clarity. And then we apply this function f, which is called the activation function. And these are some examples of activation functions, like the sigmoid function at the top and the rectified linear unit at the bottom, which are applied element-wise to the value in each node. So these are important because otherwise the neural network could only compute linear functions, no matter how many of these layers you have, which are pretty restrictive and limit the total representational power of them. And by adding these nonlinearities, we can avoid this phenomenon. So we've quickly gone over what a basic neural network is, and now we'll go over some extensions to them that are relevant for the task of detecting function starts and ends. So as we've defined them, the neural networks take a vector of real values and then compute a function from them into a vector of other real values. But in our case, the input is not real values, they're discrete values. And we can't just arbitrarily convert these discrete values into real values either, because I may be effectively saying things like that instruction number 2 is twice instruction number 1, which doesn't make much sense. So what we do instead is we map each possible input into a unique real valued vector, and then we use that as an input into the neural network. We also have discrete outputs for our task, and since we want the neural network to be able to make binary decisions, so we can have it output a probability distribution over the two outcomes. Right, so the process by which each discrete input is mapped into a real valued vector is called an embedding, and let's go a little bit deeper into how those are used. So binaries consist of sequences of instructions, but at a lower level, you can just view them as sequences of bytes. So what we have here is that we map each of the 256 possible values that a byte can have into a different real valued vector. And then we use this vector as the input into the network, or the values for the bottom layer in the picture to the right. However, neural networks, as we've defined them, can only take a fixed number of inputs and produce a fixed number of outputs. But for detecting function boundaries, we want to be able to put in, say, a chunk of code which can be variable in length, and then also get a variable number of decisions out about whether there's a start or end to a function at that location in the code. These recurrent neural networks are, we have these recurrent neural networks as a generalization of neural networks to arbitrary length sequences. In the pictures here, we have an arbitrary number of inputs at the bottom. These inputs are connected, each connected to a hidden layer, which are the boxes in gray. And then the hidden layers are also connected to each other with these arrows that point to the right. And then there's a commensurate number of output layers at the top. So if you draw the diagrams at the level of nodes rather than layers, you get a picture like the one that you see on the right with the large massive arrows. And again, for concreteness, here's the mechanics of how the computation in this network works. The bottom boxes are labeled with x's, the middle boxes with h's, and the top boxes with y's. And then we compute each hi by multiplying xi with some weights, multiplying hi minus 1 with some other weights, and then adding them together. And then we compute yi from hi. So let's remind ourselves about what we want to do with this slide from a few slides ago. So we have the binary, and then we want to point out where the functions start with the neural network. So how might we use these recurrent neural networks to do this? It could look something like this. So we go through the binary one byte at a time, and then we just input the bytes as is. Maybe it makes sense to disassemble the binary and then input the instructions we got into the network instead, but just putting the bytes is easier, and maybe it'll work fine. And in the output, we have the neural network decide whether there was a function start at byte 1, a start at byte 2, and so on. And we can do the same for function ends as well. But maybe you can see a small problem with this approach. So to compute whether there's a function start at byte 3, you compute the value of this output labeled with a red border at the top of the diagram. But this value is only influenced by the other things that are labeled in red, and therefore only the binary the bytes at 1 through 3, and not bytes 4 through whatever comes next, ends up influencing this decision about whether to say there's a start of a function at this byte. Right, so just to restate this, in regular recurrent neural networks, each output is influenced only by the temporally preceding inputs. And if you want to use a recurrent neural network for something pretty different, where for a process that actually occurs over time, then this makes sense because you don't get to see what will happen in the future when you want to decide what to do now. But for something like this function identification problem, where we're just computing over binaries where we have the whole binary at once, this doesn't make that much sense. So the simple solution to this is just to have two parallel sets of hidden layers. One of them processes the input forwards, as we had before, and the other processes it in reverse. So in this picture, to compute the purple output at the top, we have the information propagated forward through the parts that are marked in red, and also backwards to the parts that are marked in blue, and then they're combined in order to produce the purple output. So how do we actually learn a neural network to be able to do these tasks that we want it to do? So it turns out that neural networks are fully differentiable, which means that you can compute the partial derivative of any output with respect to any parameter in the network. So given a training data set where we have examples of inputs and outputs that we want the neural network to be able to emulate, we define a cost function over these examples to quantify the error of the network on these examples at this time. And then repeat the following procedure where we compute the gradient of the cost with respect to all the weights in the network. And then this gradient tells us which direction we should move in order to update the weights so that the cost becomes lower. Then we just repeat this many, many times until it converges to until it converges. Okay, so now we'll go into the experiment that we did in the paper to demonstrate how this approach works. So as the training and test data, we used these 2,200 binaries collected for this work from last year at USENIX that I mentioned earlier. So they took a lot of open source packages for both Linux and Windows, and then they compiled them with multiple different compilers for Linux, GCC, and ICC, and for Windows with MSVC. They compiled them for x86 and also x86-64. And they compile the binaries at 4 different optimization levels to see how the results vary depending on the optimization level, or to ensure diversity of different types of binaries. So here's a picture of the full methodology with also the bidirectional recurrent neural network instead of just the version that goes forwards. We have the bytes at the bottom. We have the two directions of hidden layers in the middle, and then we have the outputs at the top. So we used bidirectional recurrent neural nets, as shown in the picture on the previous slide, with one hidden layer and 16 dimensions in each of the in the hidden layer. So in the picture, each of the gray squares represents a 16-dimensional real-valued vector. And we input the binary as a sequence of bytes without disassembly or other preprocessing, as I mentioned earlier. So we trained 8 separate RNNs for the problem so we train one network to predict start versus, so there's start versus end, and there's also Linux versus Windows, and there's also x86 versus x86-64. So each network predicts either whether there's a function store and for, say, Linux x86, Linux x86-64, or any of the other 4 combinations. And then we trained each RNN for a fixed time of 2 hours. Okay, so now I'll go into the results that we obtained on this data set. But before I go into the results, first I'll describe the metrics that we use to measure how well the system did. So we don't want to just use accuracy, which would be the total number of correct bytes over the total number of bytes in the binary, because there aren't that many functions in the binary compared to the number of bytes. So if we did something like predict that there are no functions at all, then we would get something like 99% accuracy, because 99% of the time we were right. There was no function at byte n. So instead we need to use other metrics like this precision and recall. So precision is the fraction of predicted positives which were correct. So every time we predict that there is a function here, we measure which fraction of those were actually functions. And we also use recall, which is the number of functions that we found over the number of functions that actually exist in the binary. And since 2 numbers are harder to compare than one, we just collapse these 2 into the F1 score, which is a standard metric, and the harmonic mean of these 2 metrics. Okay, so this slide shows the results compared to the previous work byte weight on function star identification. So we divided the results into these 4 different segments based on the operating system and also the architecture. And we computed the results with 10-fold cross-validation, which means that we take the 2,200 binaries, we divide them into 10 pieces, and then we do 10 experiments where in each experiment we use a different piece as the test data and the other 9 pieces as the training data. And overall, the neural networks did better than the previous work, except on one segment where it did slightly worse, but about the same. And overall, there was a 2.4x decrease in error rate. And for identifying function boundaries, we see a similar pattern, where on ELF x86-64-bit, we did slightly worse, but about the same, and on the others, we did about twice as well. And overall, there was a 1.6x decrease in error rate. And this is a comparison of the total training time as reported in the byte weight paper and with what we observed while training the neural networks. So since we had 8 neural networks and we did 10-fold cross-validation, and we trained, so our method took 80 hours in total to train. But in the byte weight paper, they report that in total that the training process took 587 hours. But if we take out the cross-validation, our method would take 10 times less to train because each of the neural networks are trained completely independently. Whereas with byte weight, there's a lot of work that's shared between each of the 10 folds, so presumably it would take a little bit less, somewhat less time, but maybe not 10 times less. Okay, and here's a comparison of the performance in terms of how long it takes to actually get all the results for the how long it takes to detect all the function boundaries within on all of the 2,200 binaries in the data set. So with byte weight, the previous work, as I described many slides ago, in order to obtain the full results that they obtained, they needed to perform a bunch of expensive static analysis after doing some pattern matching. So in total, they say that their method took 20,000 minutes approximately to run on all the binaries. In comparison, our method only took 43 minutes. So in different units, byte weight took about 14 days, and our method took less than 1 hour. And this is in terms of, I guess, core hours or computation hours. So if you had exactly one machine with one CPU, how long it would take to do all of this. So in conclusion, I think we were able to show that neural networks can efficiently and effectively solve the problem of function identification. And I encourage you to try neural networks for your next machine learning problem. Okay. Thanks.
Okay, let me ask this. In your talk, you mentioned that malware analysis as one of your motivation example.
Yes.
Have you thought of applying this one to obfuscated binary instead of this normal, well-intended binary you use for your experiment?
So we didn't have a data set of, I guess, malicious binaries with the ground truth, so we weren't able to do that experiment, but it would be interesting to see how well it applies in that case.
Kevin Bogota, UC Santa Barbara. I'm wondering, did you look into what your network actually learned? So what sequences of bytes it recognizes as a start or end of a function?
So there's some investigation into that and described in the paper. So it was interesting to see some kinds of mistakes it made. So I think one thing it learned to look for was that often the compiler insert padding between functions in order to align functions at even address boundaries. So sometimes it would make the mistake where if it saw a NOP in the middle of a function, then it would think that the next instruction began a function.
Okay, one follow-up question. Did you look into, because you're working on x86, did you look into unaligned, essentially, because instructions are not really have any alignment on x86, right? So you might have like a constant which looks like the start of a function. Did you look into how many of those you might have seen in your cases?
I'm sorry, could you repeat the question?
So on x86,
yes,
instructions are not aligned at boundaries, right? So you might have an instruction which is 7 bytes, another one might be 4, then you have one which NOPs are 1. Did you look into how many misclassifications you had, particularly on that kit, or did you just look overall?
We didn't look at the results in that way. And in general, since this just covers the bytes directly without disassembly or other kind of preprocessing, it kind of, I guess, sidesteps that issue.
So if I would be an adversary, I could possibly inject constants, which essentially, particularly, which might break up a function for your function identification, right? If I inject a specific constant which might match your end and your start, I could essentially force your function identification to fail.
Maybe it'll require some, I guess, further investigation to see the exact limits. But
thank you.
Hi, Sarah Maslin from George Mason. I got 2 questions for you. The first one is there any specific feature in this problem that you chose neural network and this specific neural network, recurrent neural network, for your problem? And why you didn't compare to other machine learning algorithms? And the second one is more into implementation. How many layers of hidden nodes did you use, and how many nodes in the hidden layer did you chose?
So as for the first question about how we decided to use neural networks, so since neural networks have been getting a lot of attention from different field of computer science recently. And as far as we knew, there was no other previous work which applied neural networks to this sort of problems. We thought it'd be interesting to see how well they would do. And recurrent neural networks, as I described earlier in the talk, seemed like a pretty natural fit for these kinds of operating on these kinds of sequences. And as for the precise parameter settings that we used for the work, there are more details in the paper about the exact numbers.
Also, if you see the process memory, there are tons of interesting data structure that you want to identify. Could you make some comment about some people who want to apply this technique to other type of data structure?
I imagine that if it could work pretty well for other kinds of for identifying other kinds of structures and binaries that are relatively easy to identify just from looking at patterns of instructions or bytes that occur within the binary.
Let's thank our speaker again.